Good morning to all of you. Today we are going to talk about sediment transport in river, and that part we are looking basic concept levels that how we can understand river sediment transports in rivers. Looking that these are the two books we are more focusing for these lectures. One is Stream Hydrology and Introductions to Ecology. That is the book we are following it, which gives a very basic concepts how the sediment transport process happens, and you can look at this P.Y. Julian books which talks about the river mechanics. You can see this river channels which is there in laboratory scale with the scale down models, and if you are going to increase the discharge, okay, if you are going to increase the discharge, okay, so in a channels like this which is representing this a scale model of a river. So, if you increasing the discharge and you have a bed materials are the same, as you increase the discharge, as you expected that the bed shear stress is going to increase it. Okay. The bed shear stress is going to increase it. That shear force acting on the bed, that what per unit area, that is what is going to increase it. As this discharge increases, the sediment bed shear stress changes it. At particular instance, as the shear stress increasing, what we can observe it, the sediment particles or the bed particles which are lying on these channels, they will start motions. Okay. That is what is called incipient motions. That is what is incipient motions. That means that is the periods the bed loads are start moving it. Okay. That is the incipient motions, bed loads start moving. Further, if you increase the discharge, you can see that a series of the bed materials they will move along the rivers. Okay. And if you are further increasing this discharge, what you will see that the bed materials which is moving along the bed, that what is remain suspended conditions. As remains a suspended conditions for a considerable time length, because of the increasing the turbulence characteristics, that what remains the floating of the sediment particles which will be as a suspended loads. It depends upon three considerations, that what is the flow properties and hydraulics at the near bed conditions, turbulent structures, we are not going more details how the turbulent structures happens here, and also it depends upon the sediment characteristics, that like D50, the weight of the sediment particles, all it depends upon how this bed load, suspended loads will go through as the discharge at the bed shear stress increase, if I try to understand that way. Now, if you look at next point, here if you look at the channels is moving it, and that way you can see this flow moving in the both the sides, and it's showing that how the flow structure, the turbulent structure are changing it, and how they are responsible for incipient motions, the bed loads and the suspended loads. That is phenomena, just to visualize the flow phenomena as in a scale models what we are showing to you. Now, if you look at next part, if I go to very microscopicals, okay, what it happens when you have, let be the capital U c, the flow velocity is coming it, and it has a flow depth h, and this is the bed materials which is heterogeneous bed material, mixed bed materials are there, which is a bigger size and smaller size, and this is what the logarithmic velocity distributions for a turbulent flow. So, you can see that there will be logarithmic velocity distributions, and U c stands for here is that the velocity near the particles, okay, the particles which will be the bed particles which will be detached from the bed materials, that is what is the UC, what could be the velocity because of that velocity and the flow field, it will have a lift force and the drag force, which will detach this particle from this, and once it detach it, it can go through rolling process, just rolling the bed material, or can be a sliding, can be have a slide with jumping and hopping and putting it. That is what selecting can happen. So, it can, the bed material can go as a rolling, or the sliding, or can have a selecting it, and there will be a formations of turbulence eddies, the formations of turbulence eddies. Now, if you try to understand it, that when you have the channel flow, there will be bed, and in the bed levels there will be the velocity, which we stand u c is the velocity at which the threshold conditions of sediment motions will start. Sediment motions will start. So, if you look at that, the bed materials can have a rolling, sliding, or the salting it will have a certain thickness where the bed materials will be quite significant order, and resulting of that, because of there is a movement of a bed materials with the flow, what we will see that there will be a two shear components will acting on this. One is the decomposed into two part, which is a dispersive particle shear stress, that is what is acting because of the turbulent structures, as the particles are moving it near the boundaries, we will have the dispersive particle shear stress, also we will have the interfacial the fluid shear stress. That is, try to understand it. Interfacial fluid shear stress is generally we need to have it, but here the shear stress have the two components. One is the dispersive particle shear stress and the interfacial fluid shear stress, and how does they vary along these vertical directions. That is the behavior it happens it if you consider as a turbulence flow, as the turbulence flow as you are going it. So, we are not looking much particles level, that is what is nowadays it is possible to look at the particles level and track each particles and try to know it how the process are happening it. For example, if you look at this the numerical codes which is available, computational fluid dynamics, as you may have a awareness that it has gone to a certain levels, the sediment particles, the bed sediment particles can represent as a spherical balls, as equivalent spherical balls, and if you have the flow is going like this, you can see this all the process of particles are happening it as a rolling, as a hopping, or as sliding. So, you can see the particles and how the particles are moving and also the falling downs. All you can look at nowadays is a it is available. So, direct numerical simulations you can do at the particles level and the fluid interactions and try to know it how the process is happening it. And more detail at the particle levels you can see that how the things are happening in terms of the contours and in terms of the force components what is occurring. So, that is what is present area we are working at the particles levels can be possible it, but most of these equations what is developed for sediment transports are not at particles level, they are more understanding at gross characteristics level. Let us try to understand at the gross characteristics level, not at the particles level. So, looking that I am just look at first part is what type of near bed boundary conditions. We talk about in terms of hydraulic smooth case, because as you can have a quite good understanding is that when you have a flow passing through a surface, you will have a laminar sublayer, so you will have the transitions layer, you will have the turbulent boundary layers. The same concept we can look at that when you have the surface and the hedge fluid is passing through that, we can find out the thickness of laminar sublayers. If his height of the roughness is k, then if this height of roughness is k, okay, that is what in terms of D50 or D85 we can represent it is you know this bed materials I can measure is what will be the height of roughness. Okay. If the thickness of laminar sublayers is larger than the height of roughness k, then we call hydraulically smooth layers. Okay. In this case, the surface irregularities are small and totally submerged in the laminar sublayers. Surface irregularities become very small in comparison to water depth, But if you look at the cases which is so often happens in the river flow, which is called hydraulically rough conditions. That means the roughness heights is more than the height thickness of laminar sublayers. Okay. Thickness of laminar sublayer. Because of that, you can see this eddy formations what is there in this case and this case will be the different, because the surface roughness whatever is there, they are beyond this laminar thickness of the laminar sublayers. They are inside the transitions layers. Because of that, the flow turbulent structures, that is what will be changed. And most of the river conditions we have hydraulically rough boundary conditions. We have hydraulically rough boundary conditions where the height of submergence is larger than the laminar thickness. Now, if you look at in terms of, if I try to define it, is the relative roughness, that means I am talking about if I have the d is a depth of the flow and the k is the roughness heights. Okay. K is a roughness height, maybe the boulders, maybe small sands. Okay. So, if the roughness thickness we can define as relative roughness, which will be k by d. Okay, k by d. This ratio indicating is that what is the k and d values, and which talks about in terms of the laminar sublayers in terms of where it is lies, that if you look at this k relative values, which is a function of a simple ratio of k by the d value. So, k is a measure of the roughness, basically the particle diameters, and d stands for here is the water depth. This roughness height k is varies a grain size distributions of stream beds. Okay, whether you have a gravel bed, you have the sand bed. So, this roughness is varies. The roughness elements are projected into the flow. The arrangement of smaller larger roughness elements also the plays the rules. Okay. What we try to do is that as you all aware about the Reynolds numbers, which is a ratio between inertia forces by the viscous force, the same the two force components we can look at that defining the roughness Reynolds numbers. Okay. Roughness Reynolds numbers, here this inertia forces we are replacing with the V stars, which is a shear velocity. Here again I will say that what is a shear? It is a shear force in unit of the velocity. That is what we are defining it to make it a non-dimensional form of Reynolds numbers, which will be a roughness Reynolds numbers, which will be defined in terms of the shear velocity. As you define is a, what is the shear velocity? It is actually shear forces stresses per in terms of velocity unit. That is the reasons we divide by the rho and do the square root, which will have the unit is meter per second. Okay. So, tau is a shear stress acting on the surface and the rho is, as you know, it is a density. So, if you look at that, if you compute the roughness Reynolds numbers. As we know from a pipe flow, we separate between laminar flow and turbulent flow based on the Reynolds number thresholds. The exactly same way in case of the channel flow, where we have the bed roughness and we can compute the roughness heights in terms of particle diameters, we can compute the shear velocity, and we know the kinematic viscosities of the fluid. We can compute roughness Reynolds numbers, and if the roughness Reynolds number is lesser than 5, lesser than 5, that is again I am to rewrite it, is a V star is a shear velocity times of K stands is a measure of the roughness height by this kinematic viscosity. It indicate for us, if we have hydraulically smooth, this value will be lesser than 5. So, that means it will be the 5 times then these values, to try to understand it. If I have a this roughness Reynolds number is greater than 70, we have a hydraulically rough conditions. That is what so often in a river systems we have a hydraulically rough conditions, because most of the conditions it prevails, or we can have a in between. That is what is the range of roughness Reynolds numbers between 5 and 70. So, now we will try to understand, we are hypothesizing this at the near bed boundary conditions to know it, is it a hydraulically smooth or hydraulically rough conditions, hydraulically smooth or hydraulically rough conditions. That is what we decide as we decide the in pipe flow the laminar turbulence, or open channel flow laminar to turbulent zones. The same way we here define it in terms of roughness Reynolds numbers, in terms of roughness Reynolds numbers. When the roughness Reynolds numbers is more than 70, we define is a hydraulically rough conditions. That is the conditions where you will have the thickness is a larger than the thickness of laminar sublayers. Now, if you look at how does it happens, not at the particle size, it also depends upon arrangement of the particles. It also depends upon the how the flow patterns happens it. So, it is a combination of your knowledge on fluid mechanics. You can try to understand how it happens it. Like for examples, if I have the roughness, K height is apart by a distance of lambda, lambda is a distance apart between these two roughness height. When you have the flow, what it actually happens is there usually be turbulence zones, no flow or low velocity zones, and there will be eddies, there will be still. So, if you look at that, when you have this lambda is much larger than the K value, you can see that in that case the eddies which is there generated by the first roughness does not affect that flow structures to second one, the next one. So, it is a reach. So, K by lambda value is small, or the lambda is much larger. So, we are representing the bed roughness as a equivalent of the K height, and they are spacing at the lambda distance. They are spacing at the lambda distance. Looking at the flow pattern behavior wise, the eddies which is formed by this one, it is dissipated by the time it reaches to the next one. That is the basic idea. But if you have a wake interface flow, so again the lambda if you decreases, that means what will happen it will interpret. So, that means whatever eddies forms are there, that what interact with the next one. The next one is interact with the next one. So, they are not independent like isolated cases, Now, we have a wake interfaces flow conditions. Okay. You have the lambda length, they are interfacing each others. Okay. They are interfacing each others. The eddies from this element interact it, causes the intense turbulence. Okay. The turbulence degree will increase it. The surface will have a considerably the rough surface. Okay. Considerably rough surface. Now, if you look at the next part, what I am showing it that if you further lambda, if you decrease it, it is that the case will the flow like a skimming it. That means, you will have a zones where the flow will have a not have a much eddies formations, but they can go off. Okay. As and there are the flow structures which are not more going to affect much the eddy structures. So, that can be conditions. There will be low velocity eddies occurs in the groups. Okay, that is what is there between the element, and k by lambda is value is high here, and the flow skims over the tops. Okay, flow goes over the tops, and these are the low velocities eddies formations will be there. Or you can have a exposed roughness flow, okay, skimming flow. In that case, that is what it happens many of the smaller rivers. If you have the big boulders and all during the low flow, you can have a flow, water flow can over and around these large obstacles, and it can perturbate it, it can have a flow separations, the eddies formations and this. These are understanding we should have it, how the roughness behaviors are coming it, how these aquatic habitats are there in a river systems, if you are trying to understand that. Now, let us talk about velocity distributions. As we discuss, it's follow the logarithmic distributions. If I plot between distance from the bed, okay, this is the bed, and if this is the velocity, I will have a viscous or laminar subledge, and if I have the turbulence zone. That is what we discussed very beginning. Linear part is a viscous sublayer part. It is a linear part of velocity distributions in a laminar sublayers in case of hydraulic smooth surface, followed that part by that it is a logarithmic velocity distributions, but there will be difference between observed and the logarithmic profiles. If I write the velocity distributions, the velocity distributions follow like this. U is the velocity distribution into V star. Okay. V star is the shear velocity is equal to 5.75 log of y is a depth V stars by kinetic viscosity plus 5.5. Okay. So, this is the velocity distributions equations. If you look at that, it is a logarithmic velocity distributions in terms of y v stars is a shear velocity by the kinematic viscosity values. So, we can find out the u is the velocity at the y distance is a functions of a logarithmic velocity functions, we can make it. But in case of hydraulically rough, as we have discussed the hydraulically rough zones, in that case there is no laminar sublayers, and this closer to boundary this velocity distributions we predicted from the velocity what we get it as a logarithmic profiles, as a logarithmic profile of the velocity distributions v versus and the y. Okay. So, that is what is the hydraulic rough. So, the velocity distribution, and if I write the velocity distribution as I written there, the same form, okay, the ratio between the velocity at the y by the shear velocity will have the functions of same way 5.75 the log here we have the in terms of y by k. okay, the depth by the roughness heights plus will be 8.5, or we can simplify it, that is u by p stars, the ratio between flow velocity by and the shear velocities. If I simplify these equations, we can get it 5.75 log 30 y by k. Okay. So, that is a quite interesting, and these distributions already whenever we conduct the lab experiments, we have seen that in case of the turbulent flow, it follows the logarithms, and more or less the same equations is follow it with having this. Here the parameters is y by k, and here it is a in terms of y into v stars by mu, which is a form of the Reynolds numbers. Okay. Y is a depth of the flow, but in case of when you talk about the hydraulically rough zones, the velocity distributions not depends upon the viscous force components, it depends more on relative roughness values y by k, the relative roughness values, and that is the logarithmic profiles. That is what is the logarithmic profiles as it approximates like this. So, this is what the velocity distributions when you have hydraulically smooth surface and hydraulically rough surface. Now, let us go to very interesting part, how does the sediment transports happens it? What is the distributions of sediment transports? Okay. Earlier also we discussed it, but just to have to this, because the velocity distributions as follows is a logarithmic distributions, the sediment particles are near to the bed can have a bed load like this. There is a certain thickness where you have a bed load, beyond that you will have a suspended load, okay, suspended bed material loads. Okay. It is all these bed materials which are there goes as a suspended levels, it remains in suspense because of turbulence lift and also the buoyancy forces, the both it is a lifting that suspended particles, okay, that what will be exponentially decayed as we go from the bed to the free surface. This is what the free surface, this is what the distributions of bed load and the suspended bed material loads. And sometimes we have the wash load, which is a very fine particles, can be a very uniform throughout this depth, okay, throughout the depth it is a very uniform, and if you put it all we will have a total sediment loads. Okay. Many of the cases we do not talk about this wash load, because wash loads does not, it is a very fine silt contents which are not much effectively in terms of morphological change. We talk about the total load, which is a summations of bed loads and the suspended load, bed load and suspended load. Okay. So, more upon we neglect the wash load components. Okay. So, please try to understand it, how the sediment concentrations vertical distributions, okay, bed load, suspended load and the wash load. If you consider the wash load, the total diagrams will come like this, but total load for morphological point of view, if you look at it, we have a combinations of bed load and the suspended load. That is the concept what we follow it. And now, if you look at next part, how it happens at the river levels, as river has other cross sections like this. Okay. And you can see that velocity distributions will change it as you go to the center points. Okay. It is the flow directions. Okay. The velocity distributions will change it. The sediment concentrations, if you look at that, what is follow exponentially decay. Okay. So, value is like this. Okay. So, I will be high and exponentially it will decay it as go up. Okay. The sediment discharge, which is talking about the sediment mass for per times, okay, that is what is a multiplications of the discharge and the sediment concentrations, they will follow these diagrams. Okay. Looking these ones, I will talking about that when you talk about how complex the river systems, it is not a uniform, okay, it is not a channel. When you talk about a channel flow, which is typically we have seen it is a very simple diagrams, but when you come to a river, there are the spatial variabilities are there in terms of velocity distributions, in terms of sediment concentration, also in sediment discharge. That is the knowledge we should have, or we should try to understand how this happened. Another point I want to introduce you that the steam powers. The steam power is nothing but it is the potential energy losses in a stream if a length of L. So, that is what clear cut indicates that based on the steam powers we can know it how much of sediment transport capacity is there or the erosive power is there of the streams. That is reasons we compute it the steam powers. That is related to the sediment transport, it is related to the bed forms. Okay. It also depends upon the channel pattern, the shape of the longitudinal profiles. Okay. So, we will define the things more details. The steam powers defined as a functions of unit and QS. Okay. More details will go in the next slides. So, your steam powers defined as a unit weight, discharge and the slope, that is the friction slopes. Okay. So, if discharge increases, okay, the steam power is going to increase it. Okay. That is we can know it that, or if the slope is increasing it, also the steam powers is going to increase it. The lever, that means hilly river which is a more slope, the hilly river which is more slopes having the more steam powers with the same discharge if it flow in a valley rivers. Okay, because the slope of this is larger than the slope of the hilly area and the valley area. More the steam powers are there. That is what we define as a potential energy, but energy dissipations what is happening it with a Q discharge and all. Similar way, if I having the more the discharge, more the steam powers. The basically it is a steam power is spent in the frictional dissipations of the energy. In case of alluvial river at the boundary of the steam power used for a transporting the sediment. We will talk about more details when you talk about sediment transport. Now, if you look at how we define the steam powers, the steam powers is a if you look at the energy per unit area, that is what steam powers is defined as a product of bed shear stress at the bed into the average velocity, the mean velocity across the streams. Okay. Unit weight of waters discharge in the streams as stands for energy slopes, that is what. But if you are looking at the unit staff or in terms of unit mass of the waters, okay, just you divide the mass of the waters is rho into volume, that will be give it in terms of this the steam powers watts per kg, that is what will come towards as a GVS. V is the velocity, you can consider the mean velocity, S stands for the friction slope which considered the energy time rate of head losses over a reach where the head of energy per unit weight. How much of energy losses are happening it as we have the steam powers. Okay. Now, if you look at what it actually happens, it is that. So, as a river, okay, it is a longitudinal profiles, okay, this is the length and this is the elevations. Okay. What it happens is, as we are going to more the downstreams, okay, we expected it that discharge will be increased. Okay. That is what is in general. Okay. As you go downstreams, you will have more increase of discharge. Also, that what will facilitate to increasing the more stream powers. That means, the energy dissipations are much more necessary as you go to the more the downstreams. Okay. But because discharge steam power per unit area is a typically decreases as the slope decreases. But as we know it, as you go the downstreams, the slope is also decreasing trend. Okay. Slope is a decreasing trends. So, if you look at this, as I go from the river from upstream to downstreams, the discharge increases, slope is a decreases. And that is the reasons what the hypothesis we have, river is trend, shape of the streams is always two opposing tendencies. That is what is Langbein and Leopard 1964. It is opposite tendency, that energy to be expended uniformly over the length of streams. Okay. Stream, the river, it tries to make it such a way the cross section and the longitudinal slopes, transport slopes such a way that it will be tried to expand it or dissipated uniformly along the streams. Okay. Or it will have a constant stream powers, or it can look it always river will try to minimize total energy expenditures over the length of the streams. Based on these two hypotheses, we have a lot of studies what we discuss about the lens concept and all they follow these two hypotheses which opposing tendency, that is what is derived by observing the river how it is happening it. Headwater streams, the hilly streams where the discharge is low, slope is high. When the valley streams you have a discharge is high, you have the slope is, thus the product of QS remains relatively constant along the river of the stream. That is the concept what is there. The energy to be expended uniformly or making a constant stream power will happen it from this headwater to the valley, because in headwater discharge is low, slope is high, but at the valley streams you have a discharge is high, you have slope is low. So, it tried to make it the product of QS, which is a stream powers, remains relatively constant over the length of the streams. That is river try to adjust toward that. That is basic concept of the river. We derive it for these studies which is available on this paper. So, what I am just looking at that if I have a 700 kilometer length of the Brahmaputra rivers starting from river reach all the data 700 kilometer length, and this is the elevations. If you look at that how the bed slopes are changing it, this is our original data. Okay. These are the bed slope how it is changing for a 700 kilometers of the Brahmaputra rivers. How these the high flood levels are changing it. But if you look at the steam power per unit braided belt per unit width, that is what is changes like this. It is quite interesting that steam powers are varying it, and that is what is varying from 1940s, 1970s and this one. So, river is try to have a, as I am giving examples of the 700 kilometer length of the rivers, the Brahmaputra rivers from starting from Sadia to Dhubri. you can see that how these rivers, the stream powers are there, the energy dissipations are there, the potential energy difference is there per unit width. That is what is a very interesting slide indicating how these energy dissipations happens it, because it is all related to the sediment transport mechanisms. Okay, let us discuss about the bed forms. Okay, the river beds are not the flat bed. Okay, and as we increase the discharge or changing the slope. Okay, you can have the two conditions, either the slope of a channels we can change it, or you can change the discharge of a channel, river channels, the plume in a laboratory levels, or that what kind of conditions where the slope is changing and the Q is changing it, we are increasing the stream powers. Okay. As it increase the stream powers, bed material start moving it. Because of the bed material moving, particles are starting it, they forms a different bed forms, the different bed shapes it's formed. So, that what we are looking at as the stream powers increases in a plume, we can understand it, or if you go to the field you can see this river bed forms. Okay. When you have a typically a flow proud numbers is much lesser than 1. Okay. In that case you will have a bed form with a small amplitudes, okay, with very small amplitudes, and this thickness is not bad. So, the sand particles will make a small type of ripples, okay. Patterns will form it, ripples patterns will form it, which will be as the velocity increase, moment of starts it, and that is what it will make it as a patches, and the clustering of particles they are oriented to make a series of ripples waves. Okay. Initial bed forms, then we will have a series of the ripples forms. The smaller congregations in the bed with a sharp crest, okay, and you have a sharp the crest, and if you have a further increase it, okay, if you have the further increase of the flow, if you look at this, ripples will form like this, okay, will form like this. So, that was the dunes with ripples. Okay. That is you can try to understand it when you have the channels and you are increasing the slope or the increasing the discharge. You can see it that initially will be a flat bed, then it will come with the ripple patterns. Further, if you increase the discharge or the stream powers, you will have a formations of the flow like this, okay, formations of flow like. So, that will be the and the back side of the eddy domes, there will be eddies formations will be there, and that what is the ripples will be under hydraulically smooth conditions, and the wavelength is depend upon the particle size. Okay. In the ripple case, the wavelength of these ripples, that is what it depends on particle size independent to the flow depth. But in case of the domes, you will have a hydraulically rough conditions will come it. Okay. So, if you look at this further, if you increase, you will have the dome shapes, okay, the shape you try to understand, like the sand dunes in the desert. Okay. That the same conditions happen in the river bed levels. Okay. River bed levels you will have the domes formations, as you have seen it, the domes in desert, the same conditions will happen it, and you will have the eddies formations back of that. That is the hydraulically rough conditions will prevail it, and larger the rounder crested than the ripples, and the size it depends upon the flow depth and the particle size. Now, it depends upon the flow depths, and because of this sand dome formations, there are the boils will be there, there will be vertical vortex presence will be there. If you further increase it, okay, and the flow proud numbers coming closer to 1, then these domes will be washed out. It will have a transitional zone, which is a lower to the upper zone of the stream power increased. the flow parameter numbers appears to the close to the 1, the refill and dunes will be washed out, that is the conditions will be. Again it will become a plane surface, again it will come as a plane surface. Now, if you look at the next ones, again this plane bed surface you can see it, okay, when the flow parameter numbers closer to the 1, okay. Flow parameter numbers is closer to the 1, you will have the plane beds. When you have the D is a much smaller than 4.4 mm, but if are not that is conditions, you can have the standing waves, that your shape of the wave formations of the sand and the water shape will be the same, okay. That will be the standing wave type of conditions will come it, where is a larger sediment size and the water surface and bed surface, the wave, that is what is synchronized it, and both the sand and water waves are stationary, okay. They will move like a same, the water wave and this sand wave, okay. And that is what it happens it when you have a flow parameter numbers is closest to the 1 or it is equal to 0.84. Further if you look at, okay, further if you increase the flow parameter numbers, okay, greater than 1, okay, what actually happen is, if this is the bed, it cannot sustain this the standing wave. So, it will be start it and fluxing it these waters and come back it, okay. So, that is a antidunes, that is what antidune formations will happen when flow parameter number is greater than 1. The velocity sediment transports are high, extremely unstable conditions will happen it. You can see this, the wavelength of the range from 230 millimeter to the 6 meter, okay. It can go up to L, the wavelength of the 6 meters. Further if you increase or the if your flow parameter number is larger than 1 value, then it will have this pole and the chute regions, okay. There will be pole, there will be a chute, the chutes and the pole, the chute is accelerating zones, okay. So, if you have that, there is a large quantity of sediment will be the in the suspended conditions and the flow parameter number is much larger than that. But if I try to look at how does Manning's roughness n values varies with the bed forms. If I plot steam power versus Manning's roughness values, I will get a shape like this. I will get shape like this. The first part is refill, second part is a dune, then we have a transitional stage, then you have a plane surface, that in case of the plane surface the n value will be low. In case of the dunes, it will be the high n value, high flow resistance will be there. Then as it go for anti-dunes, it will have increases. So, n value which representing the flow resistance or the energy dissipations, it also depends upon the steam powers and the bed forms, okay. Steam powers and the bed forms. Beds are not perfectly planes, it changes its beds from ripples to dunes to anti-dunes, then you have a plane surface. All these surface, the chain of the process, what it happens it as we have increase of the steam powers, the n value is varies like this surface. That is what we should know it. That is the reasons the river makes a lot of nonlinearity when you observe the stage discharge curves, because if there is a bed is changing from this ripple to dunes to anti-dunes to flat plane surface, the n value also varies it, as you can interpret it from Manning's equations. The velocity and the flow depth are related with n values, which is simple n value variations are indicating by that. With this, let us I conclude these lectures with having these quotations from Alfred North Whitehead. Science a river with two sources, the practical sources and theoretical sources. I think river mechanics follows the two parts. One is theoretical knowledge, another is practical at the river scale knowledge. That the combinations gives river engineering in different facets. Thank you very much.